Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 4.1.4. Now we're going to be looking at finding multiplicative inverses among infinite polynomials, which we can call as power series, a sum of powers of x as they keep on going up and up and up. So we just dealt with polynomials, and actually polynomials are power series. Because take any polynomial at all and notice that eventually you can just have lots of zeros, right? Zero coefficients. And so really any polynomial can be thought of as a power series. Okay, so let's take a look at an example to help us, but this is an example of just multiplication to kind of help us get started, multiplying two series together. Now, to simplify things, we can just think about this like mod out by something and just look at the multiplication when we mod out. When we mod out by x to the sixth, that means we take everything, like all powers before x to the sixth, so up to x to the fifth, and in our polynomials, we multiply those together, maybe via a tabular type multiplication method here, and we get this. Now we circled 1 plus x. That's because of the next line right down here. What if we were to if we mod it out by x squared instead? That's like 1 plus x times 1. Notice that you end up getting 1 plus x. Well, if you look at the result here, when we mod it out by x to the 6, it's 1 plus x is the result when we mod the result by x squared. So whether we did it x to the 6 or x squared, cutting it off, notice that the first bit agrees. It's compatible. No matter what mod we use, the multiplication is very compatible here. Even if we went up to x to the 9th, notice that the first up to x to the 5th agrees with what we had over here up to x to the 5th when we mod it out by x to the 6th. So this compatibility idea we'll use when we do inverses. So if we want to find the inverse of a polynomial like 1 minus x, we can do this one mod at a time. Let's start with x to the first. Now x to the first, notice first of all that 1 minus x is like 1 mod x to the first, which has an inverse of 1 anyway. So wait a minute. So its inverse, it's called the inverse p of x, is going to be 1 mod x. That means no matter how high we go up, it'll always start with a 1 plus something or other. Now, let's go up to x squared and just do this by inspection at first with a difference of two squares. 1 minus x times 1 plus x gives you 1 minus x squared. Just kind of thinking about that, how to get close to x squared. Difference of two squares is nice here because you have 1 minus x squared. Modding out by x squared gives you 1. That means that 1 plus x will look like what the inverse will be in the first two spots. Okay, up to mod x squared, 1 plus x will be it. So notice that goes back to 1. So we have a 1 here, 1 plus x. So down the line as we keep going, it'll be 1 plus x plus something else. Now, we could keep going by inspection or observation, but let's actually think about a process that we might be able to use here. Let's use target inversion. Okay, so if I use target inversion, what we could do is we could say, okay, we start with 1 minus x, which I will rewrite as negative x plus 1. And we want to multiply this by something to get us close to, let's say x cubed, if we're modding out by x cubed, something close to x cubed. So what times what gets us close to x cubed? Let's see. So this, well, we just do this division here, and we get negative x squared, multiply that. So let's see, so that gives us positive x cubed and negative x. So we were just comparing the leading terms. Negative x times what is x cubed? We got that, so we're multiplying. So we got negative x squared times that is this, so we can multiply it to the 1. And then we subtract this off. And so then we get x squared, and then we repeat the process it's a similar deal here, but we're just lowering the power down. That times that and give you x squared minus x. Notice this is the same thing as we have here. We just kind of down the powers. Actually, that should tell us a nice pattern here as we go. So this will be x and going down a power. We're going to get a -1. There, now we can keep going. Let's see, -1 times that, and I'll just go down to this line here to give us x -1, and we subtract, and we get 1. Now the remainder that we get, that means that this times this plus that remainder gets us to x cubed, meaning that this plus this is actually 1 below x cubed, meaning that this times this actually gets us to -1. So we have negative x plus 1 times negative x squared minus x minus 1 actually gets us to -1. But to get to 1, you need to multiply by -1. So it's this times this, which ends up just being 1 plus x squared. And we notice a nice pattern that we did this. Even if we replace this with like a 5, we could kind of see what would be happening. We would just be getting the same kind of decreasing sequence of powers, all negatives here, just going down. And but we know we're going to be multiplying by a negative to make them all positive. So it's kind of think we have 1 plus x squared. So we can kind of think in our minds that the inverse will look like this: 1 plus x squared. It worked. So then the next guy will carry this same thing as we go up, and it'll be plus x cubed. And then the next mod will be x to the 4th, and so forth, forever and ever. And we did this by looking at a pattern, thinking of one mod at a time. So if we have an inverse power series, it'll also be the inverse when we mod out at each mod. And that's something instructive to realize as we move along. Okay. Now, in fact, noticing that there's an effective way of determining if an inverse exists. It exists of a power series if it exists at each mod. So we have to be able to take the inverse at x to the 4th, x to the 5th, and so forth. Now, notice when we take inverse at a mod, we're taking like an x to the something or other. The only way that we can have an inverse is if our original polynomial that we're finding the inverse of doesn't share any common factors with what we're modding out by. Well, the only factor really that we can work with is x here. So basically, it can't have x as a factor. What does it mean for x to have a factor? That means that we have something like x plus x cubed minus 4x to the 5th. Notice in this case, we can factor out an x. That's because there's no constant term. It's 0. So if there's no constant term, we can factor out an x. Well, if we can factor out an x, then it shares a common factor with what we're modding by, which means it doesn't have an inverse. If it doesn't have an inverse in that mod, then it can't have, the whole power series can't have an inverse. So we have a nice criterion. Things have inverses. Polynomial, so series have power series, and polynomials have power series inverses if the constant term is non-zero. All right, let's take a look at an example calculation right here as we move along. All right, down here, so you can kind of look and read this bit. This just kind of gives you another sense and feel for how this is working. And you can even look at a geometric series idea in order to get the inverse of this as well. We're going to take a look at example 7 here. All right. Now this example actually uses target inversion. Now target inversion is really nice with polynomials because you know exactly how many steps you're going to have. Because every time you have a step, you go down a degree, at least. And so if you have like right here, we have a x squared. So we go down to degree 1, then we go down to a constant, degree 0, and then we're basically done because we just multiply by the reciprocal. So we have like 2 steps in a target inversion in order to find an inverse. Kind of nice. And it has an inverse because We have a 7 right here, so that's kind of nice as we go along. So let's see how this would work. This you can right click on this and go here and actually see this in action and see it working. Let's kind of talk about kind of what's happening here here in this framework. So we have this F represents what we're modding out by. So notice in the target inversion process that we did above when we were just dividing, kind of to see kind of what we were doing. It's the same idea. We take we divide our polynomial into our mod, and then we get a quotient and remainder. So why don't we illustrate that right here? Okay, so we have original polynomial. Let's give original polynomial a name like A. So we start with A, and then we divide. So kind of what we're doing is we're saying A divided into F, and we get a quotient. Now the quotient here is going to be represented in the code by, at this point, as step 1, 0. And then we end up getting a remainder. Now, the remainder is not the mod that we get to, because the remainder is actually how much below we are from F. And so we take negative of that, and that's negative step 1 with a bracket 1. And then from there, we take this and we repeat the process. We divide this into F again, try to get close to it. And the quotient that we get there is going to be step 2, 0. And then when we end up here is we get a remainder, but we're going to take the negative of that remainder, negative step 2, 1. Okay. And then to finish this off, we need to just multiply by the reciprocal of this, which is actually seen right here. We see how we have the reciprocals, so we'll just kind of go down here, see that right there. So basically, notice that's what we're doing. We're taking step 1, 0 times step 2, 0 times that, and this will give us the remainder. And as long as depends on which end we've chosen, we've actually found the inverse in that particular mod, or at least that is compatible or agrees in that mod. And so doing that, the code then prints out what's happening and what's going along. You can experiment with that. And even if you like, you can kind of play with the code a little bit so it outputs maybe the polynomial times the result. And you'll notice you're going to get, and notice in that case, you're going to get 1 plus something that will mod out and go away with that particular n when you mod it each time. That's maybe something to realize as well. But this is very simple code for finding the polynomial inverse or the power series inverse as we go along. And that concludes this little subsection. Thank you for watching.